Welcome back to the second video for TEC 240 on Wednesday, February 24th. In the previous videos and class sessions, we've talked about a lot of the concepts and pieces and parts that are required for generator action, or how to induce a voltage in a conductor. In this video, we're going to take all of that and put it together and talk about how we can actually make and operate an AC generator. So I'm going to go ahead and share my slides. All right, let's go ahead and get started. And to begin, let's talk about some terminology that we're going to use for the remainder of the discussion for generators. I like to separate the terminology into the physical or mechanical terminology and the electrical terminology, all right? And the mechanical or physical things are the terms, the components that you can see, all right? So when I showed you that example of a hand crank generator in the first video, you saw that something was around the outside and something was rotating on the inside, right? So we call the thing that's rotating, we call that the rotor. It's an appropriate name, right? So the rotor is whatever is rotating and the stator is whatever is stationary. Oftentimes, the rotor is on the inside and the stator is around the outside, but it wouldn't have to be that way. You could actually have the rotor rotating around the outside. It's called a can rotor, and it can be rotating around the outside, and the stationary part could actually be inside. But that's pretty uncommon. The only design that I know like that is a certain type of small wind turbine, like a residential small scale wind turbine. It's pretty uncommon for most types of generators, but something is stationary, that's the stator, or stator. I usually say stator, but either one. And something is rotating, that's called the rotor. So those are physically what you can see. Now electrically, there are two different components that are required. First of all, you got to have a magnetic field. And we talked about that as one of the three requirements for generator action, right? You got to have a conductor, you got to have a magnetic field, and you got to have relative motion between them. So one of those things is the magnetic field. So we can just call that the field for short. And then the other thing is the conductor, which we're going to call the armature. So this is the coil of wire where the voltage is induced. All right. It's important to note here that the armature and the field, either one, could be on the rotor or they could actually be on the stator. And so far in our fundamental prototypical generator, we have drawn the armature on the rotor, right? We've just drawn that single coil of wire and imagined that rotating inside the magnetic field. And that was the exact same thing I showed in the hand crank generator earlier in the first video as well. So far in the past class or two, we've been thinking about the armature on the rotor inside the magnetic field. So the magnetic field has been stationary and the armature is on the rotor inside the magnetic field and it's rotating, all right? But there are lots of different variations. There are lots of different ways to do this. All you really have to have is a conductor, a magnetic field, and relative motion between those. So you could put the armature on the rotor or on the stator, and you could put the magnetic field on the rotor or the stator. And I'll show you some examples of that in just a little bit. And there actually are some advantages to doing that, and we'll talk more about that in just a little bit. All right, so just remember, I just said this, but we've said it before. This is really important. To have a generator, you gotta have three things, and those things are the magnetic field, the conductor, and relative motion between the magnetic field and the conductor, all right? Now I'm gonna show you a quick video. It's only about, well, I'm only gonna show you about 2 minutes of the video. And I have to admit, the video is a little bit antiquated. That's an understatement. This video is from the 1940s or 1950s, and it was produced by the Department of Defense. But I gotta tell you, it is a really good video, and it really shows the basic principles of generator action. And I have not found another video that I think does as good of a job as this video that was produced many decades ago. So I'm gonna switch over and I'm just gonna show you a couple of minutes from this video. Okay, don't laugh. I told you it was an old video, but it really does a good job of showing the principles. All right.
All generators produce AC internally. In this basic AC generator, the arms of the loop cut lines of force in opposite directions, causing electromotive force of opposite polarity to be generated in the conductor. To maintain the AC character of the output in this generator, we use slip rings instead of the commutator segments used in the DC generator.
All right, I'm going to pause it right there. It's kind of hard to notice, but if you think back to the hand crank generator that I showed earlier, here is the coil of wire, otherwise known as the armature. And this coil of wire is directly connected to these slip rings. These are called slip rings. And what I want to point out here, it's hard to tell, but these slip rings are actually rotating with the armature. All right, so those slip rings you can't see because it's not obvious, but the slip rings are actually rotating around with the armature. Meanwhile, these brushes, these are not actually rotating around. They're stationary and they're just riding on the slip rings that are rotating around, and the electricity is being conducted from the armature through the slip rings to the brushes, which are stationary, and then out to the rest of the electrical grid.
This use of slip rings is the only structural difference between AC and DC generators. One complete revolution of the armature will produce one cycle of alternating voltage. If the armature rotates once each second, the frequency of the alternating electromotive force or voltage is 1 cycle per second. 10 mechanical revolutions of the armature per second produce a frequency of 10 cycles per second. Frequency, or the number of cycles per period of time, is directly related to the rotating speed. In this example, the 2-pole machine used has one magnetic field. As the armature makes one revolution, one magnetic field is traversed. Adding another pair of poles adds another magnetic field. Now there are 2 magnetic fields. The armature moves through one field in half a revolution. In one complete revolution of 360 mechanical degrees, the armature passes through 2 fields equal to 720 electrical degrees, and 2 cycles of AC are generated. Frequency can be changed in the AC generator by the introduction of additional magnetic fields. The relationship between mechanical and electrical degrees depends on the number of poles in the generator field. In a 4-pole field, we saw that 360 mechanical degrees equals 720 electrical degrees, a ratio of 1 to 2. In a 6-pole field, the ratio is 1 to 3, and so forth.
All right, I'm going to pause it there. So hopefully that kind of made sense. It talks about ratios between the electrical field and the mechanical rotations. We're going to talk more about that. So if the numbers and the ratios didn't quite make sense, that's okay. We're going to talk about that some more. And I'm going to give you an equation that we can use to make this relationship between the output frequency and the number of poles in the machine and the physical rotation speed of the rotor. Okay, back to the slide presentation. All right, so the parts that I wanted to show in that video, that I actually stopped the video for, are the slip rings. And these are the slip rings right here. These are rotating around with the armature. In fact, they're permanently attached to the armature. On the hand crank generator earlier, I pointed out those wires that were physically connecting the armature to the slip rings. So those slip rings are physically rotating around with the armature, and then the brushes ride on top of those slip rings and conduct the electricity from the rotating domain to the stationary domain where it can be connected to the electrical grid. All right, and we did this last time. We plotted what the output would look like, and we did this at a couple different points: at 1 full turn, at half a turn, a quarter of a turn, and 3/4 of a turn. All right, so we plotted what the output voltage would look like as our armature makes one complete rotation in a two-pole magnetic field. Two poles, one north pole, one south pole. That's a two-pole field. And what we said is that with one complete mechanical rotation of the rotor, we get one period of a sine wave. And this is a sine wave. So this is the output that we talked about last time in the last class. What we're going to talk about now are three-phase AC generators. So in contrast to the output that we talked about so far, where you just got one single sine wave that repeats over and over again, with a three-phase generator, which are very, very common, you've actually got three outputs, and each output is a sinusoid, and each sinusoid is offset from each other by 1/3 of a rotation, or 1/3 of a period. All right, so the output of a three-phase AC generator looks like this. And like I said, this is really common. Basically, any generator that's larger than like a household backup generator, anything larger than a few horsepower or a few kilowatts is going to be a three-phase generator. They're just really, really common, way more common than a single-phase generator. And the output that we want looks like this. So I literally have three wires, probably plus a ground wire. So like three wires coming from my generator, call them phase 1, phase 2, and phase 3, or sometimes you call them phase A, B, and C. Doesn't matter what you call them, but you got three wires coming out. And in this case, the outputs of the different wires are color-coded. Phase 1 is in black in this drawing, phase 2 is in red, and phase 3 is in blue. Doesn't matter what we call them, but the important thing is that the output of each phase is itself a sinusoid. It looks just like the output from the single-phase generators that we talked about before, but now there's three phases, and each phase is offset from each other. Notice here we've got a peak for phase 1, and then 120 degrees, which is 1/3 of a rotation, all right? Because one full rotation is 360 degrees. Divide that by 3. 360 divided by 3 is 120 degrees. So 1/3 of a rotation, you have the next phase that has a peak. So 120 degrees after phase 1 has a peak, phase 2 has a peak. And then 120 degrees after that, phase 3 has a peak. And then it would repeat. Phase 1, then phase 2, then phase 3, and so on and so forth. This is really, really common, like I said. In fact, if you look at transmission lines, like as you're driving along the interstate up to Chicago, and you see a whole bunch of really large transmission lines, you'll often see the wires on those transmission lines are in groups of 3, oftentimes. And that's because you have 3 phases, because they're carrying 3 phases of electricity. And if you plotted those phases, it would look just like this. All right. Sometimes I will note that you'll see groups of 3, wires in groups of 3, but then also you'll see a wire on top of the transmission lines. That's called a shield wire. Basically, same thing as a ground wire, but the idea behind that is that if it gets struck by lightning, then the lightning would hit the shield wire, which is just grounded, and it would conduct the lightning just down to ground, and it wouldn't harm the electric grid. So lots of times, if you look, you will see on transmission lines, the wires will be in groups of 3, and sometimes on the very top of the transmission line also you'll have that shield wire. Sometimes even 2 shield wires, depending on how large the transmission line is. So the question is, how do we do this? How do we produce 3-phase electricity? Well, if we want the output to be separated by 120 degrees, right, like this, if we want the output voltage to be separated by 120 degrees, then it's actually not that hard. All we have to do is separate the armature coils by 120 degrees on the armature. So you might have one phase A armature that might be like this. Say it's a coil that's in this orientation right now. And then 120 degrees from there, you have phase 2 or phase B, and you have a coil in this orientation. And then 120 degrees from that, I don't know, I'm having trouble contorting my hand like that, but 120 degrees from that, you would have the phase 3 armature. So if you want the output to be 120 degrees staggered, then all you got to do is take the armature mechanically, physically, and take the armature and rotate it 120 degrees from each other. So here's a picture of what that would look like. Here is the armature, and this is about 120 degrees right here. It should be exactly 120 degrees, because you got 120 degrees here, 120 degrees here, and 120 degrees here, and 120 times 3 is 360 degrees. So what this is showing is that this is the armature for one of the phases, this is the armature for a different phase, and this is an armature for a different phase than that. So you got 3 armature coils, and they're each separated by 120 degrees, and so you can imagine as they're rotating, their influence, the flux through them, the magnetic flux through those coils is going to be different by 120 degrees. So the output that you get is going to be different by 120 degrees. So this is what your armature could look like if you have a 3-phase generator. And this is what the output would look like from this armature right here. Don't worry too much about this over here. I'm not trying to show the output here. These would be the slip rings, and these would be the brushes, and these would be the loads for each phase. But all I'm really trying to show here is that, look, if you have an armature and you have 3 sets of coils on that armature, then the electrical output from that armature will be separated by 120 degrees. All right, so I've just showed a picture of a armature on the rotor, right? Let me go back just to refresh your memory. So look, the armature was on the rotor, and this whole rotor is rotating around. It's the rotating part, right? And the magnetic field, which is not shown here, but there might be a north pole here and a south pole here or something like that. The point is that the magnetic field is on the stator. So in practice, it's actually a lot more convenient if we don't do that. It's actually a lot more convenient if we put the armature on the stator and we put the field on the rotor. All right, and the reason for that is that you have to use slip rings and brushes if you have the armature on the rotor. Right? I'm going to go back a slide again. If we have the armature on the rotor like this, then we got to find some way of getting that electricity off of the rotating armature and onto the stationary electric grid. So to do that, we use these slip rings that are rotating, and we use brushes that are riding on them to conduct the electricity. And the bad thing about brushes is that they're a maintenance pain in the butt. They wear out over a period of time. Usually, it depends, but maybe once a year, you have to replace the brushes on the machine. And if you don't, then you can actually damage the machine. You can damage the brush holder, and you can damage the slip ring itself. I remember when I was working for General Electric, when I was a wind farm manager, we used to get warnings every once in a while. It was a built-in warning on the machine that would say, oh, your brush is getting low, it's getting close to wearing out. It was a built-in warning in the machine, and it wasn't an emergency. You know, when you got that warning, you didn't have to run out to the wind turbine and replace the brushes right away, but you did have to do it, you know, within a couple of weeks, or else you were going to risk damaging the machine. And it's a lot easier to replace a brush than it is to replace a whole slip ring assembly. That's a real pain in the butt to replace. And you know, we wouldn't do the brush replacements right away, but if it had been a couple days to a week before we got around to replacing those brushes, then I would get calls in my office from the fleet engineers that were keeping track of the operation of all of the wind turbines remotely from headquarters. And they would give me a call and they'd say, hey, did you get a chance to replace those brushes yet? You really need to get out and replace those brushes. And I'd be like, yeah, I know, we're going to get to it. But right now we're doing maintenance and I've got lots of other things. So we're going to get to it. Don't worry. We're not going to let the brushes wear down completely. But anyway, it's a big deal. You have to keep tabs on the wear of those brushes and you have to replace them before they wear down completely. All right, so we can get away from that. We don't have to use brushes if we swap which is on the rotor and which is on the armature. So before we've talked about so far, the armature on the rotor, and so we use slip rings and brushes to get the electricity from the rotating rotor off to the stationary electric grid. But if we had the armature on the stator, then it's already stationary and we don't have to use slip rings or brushes. So that offers a lot of convenience if we do that. And then what we do is we just put the magnetic field in the middle. It could just be a permanent magnet, like a bar magnet, a stronger bar magnet, and you put your bar magnet in the middle and you rotate it around, and that's what your rotor is. All right? So it doesn't actually matter which is on the stator and which is on the rotor. As long as you have a magnetic field and a conductor and relative motion between them, then you're going to get an induced voltage in that conductor, aka armature. So here's a picture of that. Here is an example of where we have our armature around the outside on the stator, and we actually have our magnetic field, in this case a permanent magnet, here on the rotor. So as I spin the rotor around, we're going to move our magnetic field, and that's going to get us a change in magnetic flux through these conductors right here. All right, so this is relative motion. You don't have to have the armature rotating to get relative motion. You can get relative motion just by causing the magnetic field to rotate. All right, so I could get the exact same output as I had before. I can get my three-phase output over here with this machine right here, putting the field on the rotor and the armature on the stator. All right, I will say, I'll add a little bit more to this. There's a downside to this. The downside to this is that if I use a permanent magnet like this, then the magnetic field strength is fixed. I can't change the magnetic field strength of this permanent magnet. And so what's actually fairly common is to use a design where you have the magnetic field on the rotor, but what you do is you use an electromagnet for the magnetic field on the rotor. If you use an electromagnet for the magnetic field on the rotor, then you're going to provide that electricity, right, for the electromagnet. And so you actually end up going back to using slip rings and brushes. However, even that is better than putting the armature on the rotor, because the amount of current going through the brushes and the slip rings to just power an electromagnet on the rotor is a lot lower current. It's a lot lower current, and therefore your brushes don't need to be as big and they don't wear out as quickly. So it's a good idea to put the armature on the stator, even if you are going to use an electromagnet for the magnetic field on the rotor. And that's because even if you use an electromagnet for the magnetic field on the rotor, your brushes are going to last longer than if you put the armature on the rotor. All right, does that all make sense? I know I'm using a lot of terms that might not be real familiar to you yet. Armature, field, rotor, stator. So you might need to watch this more than once in order to get the hang of what I'm talking about. As always, let me know if you have any questions. All right, and one of the last things I want to do today is talk about the relationship between RPM and electrical frequency. And that is, how fast am I spinning the rotor? Whether that rotor has the magnetic field or the armature doesn't really matter. But the question is, how fast do I need to spin that rotor in order to get the desired electrical frequency output? So what we're going to develop here is a relationship between how fast we're spinning the rotor, what is the input speed to the generator, in other words, the number of magnetic poles on the magnetic field, and the output frequency. What is your desired output frequency? So think about how we plotted the output of the simple generator last class, right? We talked about how as we rotate this simple armature, right? This simple armature, we rotated it from horizontal to a quarter turn, to a half turn, to 3/4 turn, to a full turn. And when we did that with our simple 2-pole generator, we got one full sine wave, right? This was the subject of the video as well that I showed earlier. So with our simple 2-pole generator with a north and a south, then as we do one physical rotation of the armature, we got one full sine wave period, right? And so then I mentioned this and kind of foreshadowed this last time because I said that, all right, we want to get 60 hertz output, 60 cycles per second. That's what 60 hertz means on the electrical grid, because in North America, the electrical grid is 60 hertz AC. So if I want to take that simple generator and I want to get 60 hertz electrical output, then how fast do I have to rotate that thing? Well, if I get one full sine wave every one rotation, and I want 60 cycles per second of electrical output, then I've got to physically rotate that thing at 60 revolutions per second. Or converting that to revolutions per minute, that's 3,600 revolutions per minute. Quick application, when I was in the Navy, my last ship was the USS John C. Stennis aircraft carrier, and I was in charge of the electrical generation from one of the 2 nuclear power plants. And we had a pretty simple electrical generator. It was a 2-pole generator. So guess how fast the armature was rotating inside that generator? 3,600 RPM. So it was rotating really fast. And it's not that difficult to get a generator to turn at 3,600 RPM if what's spinning it is a steam turbine. Because our nuclear power plant produced steam, all of them do. All nuclear power plants produce steam. So it produces steam, and then that steam is at really high pressure, and it spins a turbine really fast, and the output of that turbine is the input for the generator. So it's not too difficult to make a generator spin 3,600 RPM if you're driving that generator with a steam turbine. If you're trying to drive that generator with something else, I'm going to give the example of maybe a wind turbine or maybe hydroelectric turbine, then it's, desirable not to have to spin that generator so fast. But let me not get ahead of myself too much here. So first of all, I said that in North America, we have an electric grid that operates at 60 hertz AC, 60 hertz electric grid. We're actually in the minority. The majority of the world operates at 50 hertz AC electricity for their electric grid. It doesn't really matter. I mean, it's different, obviously, and your devices do need to be designed different. So in general, for most devices, you can't just take I almost said VCR. Who has a VCR anymore? You can't just take your DVD player and take your DVD player from North America and take it over to Europe and plug it in. It's not going to work. For some devices, it will work, like for a toaster or an oven or anything that just has a resistance value. Then resistors don't care. Resistors are dumb, and they'll work just fine regardless of what the frequency is. But if you take something that is sensitive to frequency, like most electronics, or a motor is going to be affected. So like take a refrigerator. Refrigerators have motors in them to run the refrigeration cycle. So take a refrigerator from North America to Europe, it's not going to run very well. It's not going to work very well. So what's actually the most interesting country, I think, is actually Japan, because you can see that it has multiple different parameters on its electric grid. So do Brazil and Saudi Arabia, but if you look closely at the key down here, what you'll see is that Brazil and Saudi Arabia have the same frequency, but just different voltages on their electric grid. And that's actually really easy to convert. Just use transformers. Transformers are really easy and relatively cheap to change the voltage. What's not easy to change is frequency. It's not easy to change your electric grid from 60 hertz AC over here and then have another part of your country that's at 50 hertz AC electricity over here. But Japan has done exactly that. And it's an interesting story. Basically, the way it goes is that the southern part of Japan, long time ago, early in the 20th century, when the electric grid was being developed, southern parts of Japan purchased electricity generation equipment from companies in North America, whereas the northern part of Japan purchased electrical generation equipment from companies in Europe, specifically Germany. And as you might imagine, looking at this graph, the equipment produced in Germany was designed to produce 50 hertz AC electricity, and the equipment that was designed and built in North America was designed to produce 60 hertz AC electricity. So a long time ago, when Japan was building its electric grid, it started by building a little grid in the south of Japan and a little grid in the north of Japan. Who would have thought that decades later they would have wanted to connect their electric grid? Because, at that time, the electric grid was only in the major cities. Well, as we all know, we have electrified our entire country, as has most other countries. And so as they built out their electric grid in Japan, there came a time when they realized, oh, we're not going to be able to easily connect these. We can't just run a wire from the north side to the south side, because you can't just connect 50 hertz to 60 hertz AC electricity. What you have to do is have a converter, and that converter station takes in one frequency, converts it, actually rectifies it to DC electricity, and then inverts it again to some other frequency of AC electricity. So as you can imagine, those converter stations are pretty expensive and they have a limited capacity. So Japan does have a limited capacity to take electricity from the north side and convert it into a different frequency and power the south side and vice versa, but it's very limited. If you think back just a couple of years, I don't think any of you were too young to remember, but about 9 years ago now, there was a pretty big event that happened in Japan and caused a disturbance on the electrical grid. You might remember that there was a tsunami which impacted the Fukushima nuclear power plant. The Fukushima nuclear power plant, was on the northern part of Japan, and when it was taken offline, that created a pretty severe power shortage on the northern part of Japan. And it was a pretty significant problem for them. And they had a very limited ability to take electricity from the grid on the southern part of the island and bring it up to the northern side, because the southern side was at 60 hertz AC and the northern side, where the Fukushima nuclear power plant was at 50 hertz AC. So just a historical little tidbit relating to what we're talking about right now. All right, so relating it back to North America for the time being, we want our generators to produce electricity at 60 hertz AC. So how fast do they need to spin? All right, so this is what we talked about just a little bit ago. If we have our very simple generator, like this one right here, where we only have two magnetic poles, we're going to call this a two-pole generator. Then if we have one rotor rotation, then our output voltage is one complete sinusoid period. If we want 60 sinusoid periods per second to get us 60 hertz AC, then we need to have 60 physical rotations of the rotor per second. And normally we convert that to revolutions per minute. So take it times 60 seconds per minute, and you get 3,600 RPM. All right, so that's great. And like I said, that's definitely applicable if you are driving your generator by, say, a steam turbine or something like that. No problem. You can spin your generator at 3,600 RPM. But that's really fast. That's a really fast speed for something to be spinning around. And so there are applications, probably two of the most common would be a wind turbine or a hydroelectric turbine, where the wind's just not spinning, the wind is not blowing that fast. So you could use a really big gearbox inside the wind turbine to take your slow moving rotor blades and step up the speed to a really fast spinning generator. But gearboxes are not 100% efficient, so you'd prefer not to use a gearbox that has that large of a gear ratio if possible. And so you'd like for there to be a way to produce 60 hertz AC output without having to spin the rotor of the generator quite so fast. And it turns out there is. There is by changing the number of magnetic poles in the generator. All right, so here's an example. Here is a two-pole generator. This is only showing the magnetic field, all right? And it's showing the magnetic field as being created by electromagnets, because you've got the coil of wire right here and a coil of wire right here. But that doesn't matter. It doesn't matter whether your magnetic field is created by permanent magnets or electromagnets. All that matters really is the number of magnetic poles on the magnetic field. So in this case, this is a two-pole machine. It's got a north pole and a south pole. And if I imagine an armature that's spinning inside here, then as I do one complete rotation of the armature, that armature goes, imagine it going from north to south and then back to north again, right? So as the armature completes one physical rotation, it is experiencing a magnetic field that goes from north to south and then back to north again, all right? And that gives us one complete sinusoid voltage output, all right? One complete sinusoid for our output voltage, all right? Now imagine I add two magnetic poles to the magnetic field, which is on the stator of this machine. And so now, instead of the armature going from north to south to north in one full physical rotation, now it goes from north to south to north, back to south, and back to north again. So what that's going to give us is, instead of just one complete sinusoid for every one physical rotation of the rotor, now we're going to get two complete sinusoids for every one physical rotation of the rotor, all right? Why? Because I've got two more magnetic field poles on the magnetic field, all right? And now instead of just going from north to south to north, I go from north to south to north and back to south and back to north. So twice as many magnetic field poles on the magnetic field. All right, so this is what I kind of just said. Now, one physical rotor rotation gives us two complete sine wave voltage cycles. And so if I were to rotate the rotor 30 times per second, I would get 60 complete sine wave voltage cycles, which is 60 hertz. That's what I want. And if I convert that to revolutions per minute, 30 rotations per second times, times 60. So 30 times 60 to convert into revolutions per minute gives me 1,800 RPM. All right. So this right here, this was 30 rotations per second times 60 seconds per minute. And the seconds cancel out, and I get rotations or revolutions per minute. All right, so that was a kind of qualitative description leading up to this formula, but now I'm going to give you a formula so you don't have to think through that, like, okay, what's my ratio of magnetic field to physical rotations? You don't have to think about that like it was talking about in the video that I showed earlier. You can just use this equation. And this equation is a very widely used equation. It's very well known. And the variables that you have to remember are in, and now I apologize, I did not create this equation, but in this equation means the generator speed in RPM. Remember, in Faraday's law, in meant something different. It meant the number of turns in the coil. But in this equation, in means the generator speed of the rotor of the generator in revolutions per minute, RPM. All right, so I apologize. I didn't create these equations. This is just the way it turned out. This is the way they're written. All right. So in is the generator speed of the rotor. 120 it's just a constant, it's a conversion factor. And F is the output frequency of the voltage in cycles per second. And P is a number of poles on the magnetic field. You're always going to see this being an even number. There's always going to be 2 poles or 4 poles or 6 poles or 8, 12, 64, 126. You know, you can do whatever silly number you want to, but it's going to be an even number of magnetic field poles. And it's important to note that as we go around the magnetic field, they're going to alternate. Just like in the picture before, it always went north, south, north, south. So if I have a 6-pole magnetic field, it would need to go north, south, north, south, north, south. They have to alternate. All right, so let's do a couple of examples here. Let's take this generator before that we looked at a few slides back. And the question is, if I want to produce 60 hertz AC output, how fast should the rotor of this generator spin? All right, so take a few minutes or however long is necessary and do this calculation. How fast should this generator spin? All right, I will assume that you have given it a shot. So think about what are parameters here. In equals 120 F over P. That's our equation, right? So in is what we're trying to solve for. That's our unknown. 120 is a constant. F, what is F? F is our output frequency. That is 60 hertz. Then we divide by P. What is P? It's the number of poles on the magnetic field. All right, and where's the magnetic field on this machine? A lot of people say when they're first doing this problem that the magnetic field is around the outside on the stator, but it's not. The magnetic field is right here on the rotor. It's this permanent magnet right here. So P equals 2. There are 2 poles on this magnetic field. So to solve this, take 120 times 60, divide by 2, and you will get 3,600 RPM. So that generator needs to spin 3,600 RPM in order to produce 60 hertz output. Note that it was a 3-phase generator, but that's irrelevant in this equation. It doesn't matter how many phases this generator is. Each phase is going to be producing 60 hertz AC output if that magnetic field is rotating at 3,600 RPM. All right. Nowhere in that equation does it say how many phases are there in the machine, right? It's just N equals 120F over P. All that matters is how fast the rotor is spinning, that's N. What is the frequency of the AC voltage output, that's F. And how many poles are on the magnetic field, that's P. All right, one more example. Let's say that the magnetic field from the previous example was replaced with this. So now we are going to swap out the previous rotor, which had the magnetic field, and now swap in this rotor with a different magnetic field. Notice this magnetic field is alternating north, south, north, south, north, south. All right, so take a minute and do this calculation. All right, and probably what you realized is that the only thing that changes is P, the number of magnetic field poles. So everything else stays the same. F is still 60 hertz. Swap in 6 for P, and you'll find that the speed of the rotor needs to be 1,200 RPM. Here's a quick application. In North America, virtually all of the wind turbines are 6-pole machines. They all have 6-pole generators. In Europe and the rest of the world, where they want to produce 50 hertz output, the most common design is to use 4-pole generators. So you can see that you adjust the design of the generator based on what you want your output voltage to look like. All right, that's going to come to the end of the section on AC generators. So I'm going to go ahead and stop the video at this point, and you are ready to do, you already were ready to do, but you can do the next lab in your lab manual now. Make sure to take a look at the schedule to find the due dates. And you can do all those problems on generators and generator theory that involve Faraday's law, and now the ones that involve output frequency and the speed of the generator. All right, so that's going to take care of things for today. Don't forget that you can be working on your DC motor design if you want to get the extra credit for that. Let me know, and I'll be happy to provide you with the materials for that. Let me know if you have any questions on any of these materials, and I'll see you next time. Have a good weekend.